Hello, friend. In this next couple of videos, we're going to get looking at getting started with neural networks. So we're going to actually see some real examples of using the Keras toolkit in order to build a neural network to do some classic machine learning problems, basically. So how you would do machine learning problems using a neural network using the Keras framework. So in this video, we're going to look at binary classification. So binary classification is probably the most common type of task you'll have to do, but also relatively simple. So let's go ahead and get started here. Okay. So for this first example where we're going to be doing binary classification, we're going to be using the IMDB dataset. So if you're not familiar with this, this is one of the datasets that's available for the Keras dataset. So these are example datasets in order to usually to teach or to illustrate different properties of how you can do machine learning with Keras. So this dataset is a binary dataset. So the idea is that it's actually textual data, as you'll see here. So we have movie reviews, and the class, the binary classification, is that the reviews are labeled as either favorable or unfavorable. So we want to build a model to do binary classification. So in this case, we're going to have 50,000, but they're evenly split between a test and a training set. And then within each one of the training and test sets, it's a completely balanced problem. So in binary classification or any kind of classification, if your training data is kind of unbalanced, you have to worry about that. But when it's perfectly balanced, then you won't have any problems with things. So here, we'll go ahead and load it. The first time you do this, I might have to download a couple of things, so it might take some time. So here, the argument means that we're only keeping the top 10,000 most frequently occurring words in the training data. So the train data and test data are really just lists of reviews, so we'll see that. So the reviews as they come in, they could be short, so maybe it's 100-word review, or there might be longer ones, 1,000-word review, things like that. So it's variable. And of course, the labels are just binary labels, 0 and 1. So you can see what those look like here. So yeah, if you look at the first review in the training data, it looks like just a list of integers. And in this case, there was like 218 words in the review, so that's where this last one came from. So it looks like a 1D tensor, so since we restricted it to the 10,000 most common words, we should find that the maximum, if you look in there, is going to be 9999. So the word at index 9999 was the largest one that we see in every one of our samples of the training data here. So these indexes are really just indexes into a word index. If you want to recreate the reviews, so for example, you get the word index and we look up a particular word. So this word index is a dictionary from a string into the index number. So we really need the reverse mapping if we want to see what this actual review is that we printed out here, right? So just a little, this little bit of code is just reversing the dictionary so that now we will have a dictionary where the original index becomes the key, and the word is the value that we have in there. So now we can do the opposite. We can look that back up. So 3475 tells us the word nuclear. Although this isn't quite correct, so actually the first 3 are reserved for some special things, padding and things like that. So I really should have subtracted 3 from there. So yeah, here, that's the actual review for in words for 1, 2, 3, 4, 5, and the actual word that I looked at index 3475 was actually typically, because we should subtract 3 from there. So I mentioned the reviews are of different length. So, the first one was 218 words, the second one was 189 words. So, that won't work for machine learning. So these are the inputs. So we want to pass in this list of words as an input, but we have to get these into some representation where it's all the same size. Okay, so this is a little bit of a preview of working with textual data, right? So this is a kind of a common pre-processing thing. So if our units of inputs are reviews here, that can be a variable length, so we have to do something about that. So we're going to use a common thing in this example. We're going to use multi-hot encoding. So basically, since there's 10,000 words total, since we capped it at that, we're going to create a vector of size 10,000 where a 1 indicates that that word was present in the review. Could be multiple times. We're not going to keep track of if that word was used 2 or 3 or 5 times in the review. Or 0 indicates that that word wasn't in the review. Okay? So you can look at this function here. You know, it's relatively simple, but we do it ourselves. There are functions in Keras and then like scikit-learn for doing this kinds of one-hot or multi-hot encoding. So the result now is that if you look at the shape for xtrain, like the first sample at sample 0, so now every one of these, the second index is just this multi-hot encoded. So there's 10, we're going to be inputting for every sample 10,000 zeros or 1, indicating whether that particular word occurred or didn't occur in the review that we're going to be doing input for training here. So we also need to vectorize the labels. So this is really just converting them from an integer into a float. So actually integers won't work as our target labels for Keras. So we just convert these into floats now. So if we look at our first 10 labels, again, this is a binary classification, so all the reviews are 1 for positive and 0 for negative. So that's typical for a binary classification task. You usually want to use the 0s for the negative case, the negative class in your classification, and the 1 for the positive case. And again, you know, just to verify this, if we look at our 25,000 training samples, it's evenly split. So we've got an equal representation of positive and negative reviews. So 12,500 each in our 25,000 here. Okay, so on to building our model using Keras. A model that performs well, this is a relatively simple kind of input data set here. Just a stack of dense layers that are densely connected to one another using the ReLU rectified linear unit activation as the output from each of the layers. And then our final dense layer, which will be the output layer, will just use a simple sigmoid, since that will squash the output activation to some value between 0 and 1. And we can think of that as the model's prediction of the probability that it's the 0 class or the 1 class in this case, right? So for models as simple as this, the only key architecture decisions are how many hidden layers or how many intermediate layers to use in the architecture, and how many units to put in each of the layers. Okay, so we'll see some guidelines, rule of thumbs later on for how you might go about figuring out what good numbers of layers and units within the layer are to use. But we'll just use 16 units in our intermediate layers. I already mentioned that these intermediate layers are going to be using the rectified linear unit activation function, but our final layer, which outputs, has just a single unit, so there's a single 1 output. So for given an input sample, it just returns a single number between 0 and 1 because of the sigmoid activation here. Okay. So in these examples, we're going to be using the Keras sequential API, which is the simplest kind of API for specifying a model like this. So sequential only supports specifying a model that's a sequential, that's a directed graph that only has one path in the graph. So everything goes from the inputs through each layer in sequence and comes out on the end as an output. Okay. So again, later on, we're going to see different kinds of Keras APIs where you can do more complicated computation graphs for a neural network here. So a little bit of a review. So recall that, I mean, each one of these layers is basically doing this affine transformation, so a chain of tensor operations. So really, each of these dense layers has a set of weights and biases, and all it's doing is whatever its inputs are, it multiplies it times the weights, and it adds on the bias term, and then it puts it through its activation function, whether it's ReLU or sigmoid. right? So the original samples, we do that transformation, and its output, so it's going to take the inputs, which has 10,000 dimensions, and it's going to transform that into an output that has 16 dimensions, because there's 16 units here, right? So that's the transformation that's happening from these tensor operations. The second layer does the same thing. It takes an input sample that has 16 features, and it outputs it again to another space that has 16 features. And then this final one is going to take an input with 16 features and output it to the final one feature output, which is the prediction that the network is making. So yeah, just, I mean, that basically means, for example, that the weight matrices in these two matrices will have a shape of, will have 16 basically values, and the bias that's being added in will also have 16 values in order to perform these tensor transformations. So the number of units in these hidden layers is important. You can kind of think about this as how much freedom you're allowing the model to have. Okay, so if you have more units, you're giving the model more freedom to try and fit the data. And if you give them less, it's going to be more constrained. Okay. So you should be familiar with the RLU activation function. You even had to implement it in one of your first assignments. So you can actually use the max function for it. There is an RELU function in the Keras set of activation functions, right? So it looks like that. Anything negative gets clamped to 0. Anything positive, you just return the value, the linear part. And the sigmoid also you should be familiar with, hopefully. That does, this is commonly used for binary classification because it maps the output into a range between 0 and 1, which is what you want for binary classification. So you'd almost always choose sigmoid activation as your last activation on the output layer when you're doing a binary classification task for a neural network here. Also recall, this is a little bit of review, that these activation functions are necessary. They are non-linear. So any kind of transformation like a matrix multiplication or addition or basic ones like that actually perform linear transformations. And the thing is that even a sequence of these, so even if we're going through multiple linear transformations, you can perform exactly that same sequence if they're all linear transformations with a single linear transformation. And so there's really no power in just doing a sequence of linear transformations unless you add some non-linearity in there. So that's one of the things that these activation functions do. They actually transform, because of this non-linear transformation, they do kind of magical things with the space that they transform from the inputs into the outputs. And finally, when you're building a neural network model in Keras, after you define the architecture like we did before, you call this function called compile in order to set up the model and get it ready for training. So the compile step, basically you provide the last pieces of information that you need. You tell it what optimizer to use, and ARM SPROP is a good default for most any problems that we'll look at in this class. You tell it your loss function. So the binary cross entropy is a type of loss function that's particularly good for binary classification problems. So we'll often choose that for binary classification problems. And you can give one or more metrics that you want to monitor during training. So we're going to give it, by default, it will always give you what the loss is while it's training the model, but we're going to ask it to also report on the accuracy, so how accurate it's doing on predicting the reviews here. So you should never evaluate a model in machine learning on the data that you're training it with. So it's really meaningless to look at the performance that it does on the data that it had seen during training. The real question is always, how does it do on data it's never seen? So that's the reason why we have validation sets and also like a final test set. So the normal practice is, if we want to validate while the model is training, we're gonna use some of the training data, set it aside. We don't train with it. We use it for that validation part to see how generalization is doing while it's training. So in this case, we're splitting apart 10,000 of the 25,000 we're holding back to do validation during our training loop here. So we've created our architecture. We did the compile in Keras in order to set up our loss function and metrics. So now we're ready to actually do the training here. So typically here, what you do when you fit a model, this is how the model learns when you pass it in your training data. So you have to pass in the training inputs, that's what the X train is here, and the training labels, which is what the Y train is. And if you want to do validation, you have to specify the data you want to validate with. In this case, we're going to be training, just have it stop after 20 epochs of training, so we'll see more sophisticated ways of determining when you want to stop your training later on. And we're going to tell it to use batches of size 512, right? So, we've got 15,000 items in our training data. It's only going to pick out 512 at a time using stochastic gradient batching and do the updates on that batch size at 512 at a time. So let's go ahead and start the training off. So this might, for a bigger model, this might take longer. It probably won't take too long here when I'm running it for this set of data here. So you can see that it's running each epoch on my system in about 1 second or so. So notice that we're reporting the stuff that we asked for. So we're reporting not only the loss, which will always be reported, but the accuracy that it's achieved after each epoch of training. And since we're giving it a validation data to report on, we see not only how it's doing on the data it's being trained with, but we get a sense of how well it's going to generalize by looking at the validation loss and the validation accuracy. So we're ultimately interested in how accurate the model can do on predicting whether it's a positive or a negative review, right? So that's kind of really our ultimate metric that we want to monitor and see how well it does with. So notice that the call to fit returns actually a dictionary that gives us the whole history of this training, so we can use that to further visualize or analyze how well it did during the training. So if you look at that, basically the dictionary just has keys for each of the metrics that are being monitored. The accuracy, this is the training accuracy and training loss, and the validation accuracy and the validation loss. If you look at this is just really the sequence of the numbers of the training loss from epoch 1 to epoch 20. Although a note about this, when you do the fit, it names these as epoch 1 through 20, but these are going to be actually indexed 0 through 19 in this case. Right? So to evaluate how well we do on training, anytime like this, it's always a good idea to look at the learning curves. So these are the plots of like the loss and the accuracy. This function, I decided to move this into the utilities for our assignments, but for example, we can use this if you look at how that plot history function is done to show both at the same time the training loss and the validation loss as it occurs over the epochs of training, as well as the accuracy. So since we were asked it to use accuracy as another metric to keep track of, we've also got access to what the accuracy was as it was training over the 20 epochs here. So as you can see here, both from the loss and the accuracy, the loss continues to go down on the data it's being trained with, but really quickly the loss on the validation data, which gives us some idea of how well it's generalizing, goes down a little bit, but then it starts getting worse, right? And the accuracy on the validation data never really improves very much. It stays below 0.9. Okay? So, you know, this is a classic example of overfitting, right? We'll be discussing this more later on, right? But this is the classic problem that you have to worry about for deep learning models. So after the third or fourth epoch, validation loss stops decreasing. So this really means that we are learning noise here. We're over-optimizing on the training data. So, I mean, an easy thing you can do with that is just early stopping, right? So if we think that we get the best performance possible after 4 epochs, we can just stop there. Right? So that's one way to fight overfitting, is just figure out where you start overfitting and only train up to that point. So let's go ahead and let that run here. So here for this final run, you know, I should point out we actually trained it on all the data, right? So even the held back validation data. We did one final model at the point that we determined where it was, you know, before it started overfitting, because we want to kind of evaluate and see how well it can do then. So it's got a little bit more data, so potentially it could do even a little bit better than what we were able to see by watching the validation while we were training. So in this case, you know, at the end, we're going to evaluate it with the completely held back test data. So we didn't use this either for training nor even to monitor for validation while we were training things up. So usually, you know, there's randomness in this, but you should usually see 87, 88% here. So, you know, not really great. It's really easy to make this quite a bit better. So state-of-the-art approaches can approach 95% accuracy. And then finally, once you have a model, so you can use it to predict stuff you haven't seen, right? So this is kind of the method, the idea of the method you would use in production, right? So once you've trained a model and you want to actually start using it to do real predictions, you can use the predict method. So in this case, what it returns is the prediction 0 or 1 for all of each of the test items here. So what you'll see is some value, since it goes to the sigmoid, between 0 and 1, right? So it's pretty confident for the second one that it's a positive review, relatively confident for this one that's a negative review, and so on. So, you know, to make our final prediction, usually you pick a threshold, usually like 0.5, and then so anything, if it's below 0.5, you'd predict it was a 0, a negative review, and if it's above 0.5, you'd predict it's a 1. Okay, so to wrap up on those, so some things you should remember from this example. So usually you do need to do quite a bit of pre-processing. So in this class, you know, we kind of jump right into doing the building the models and the architecture and stuff like that. We concentrate on that, but pre-processing steps and data collection things, those are really the biggest parts of doing machine learning and data science. So for a binary classification, stacks of dense layers with ReLU activation are kind of the basic. They can solve a wide range of problems, and usually that's kind of the first thing you'd want to try for a simple binary classification. So in a binary classification, the model should end with a single dense layer that uses a sigmoid activation, because that will give us an output between 0 and 1, which we can think of as a prediction that it's the positive or the negative class. So you should use binary cross entropy as your loss function. So that is kind of the one that's best fitted as a loss that will find good solutions for binary classification. RMS prop optimizer we'll probably use a lot. That's generally a good enough advanced optimizer for neural network and deep learning problems. And we'll talk a lot in this class about overfitting, but neural networks will eventually start to overfit. So you have to know that, and you have to always fight overfitting. And one way to fight it is just to do some experiments to figure out when overfitting begins and just stop training there to get the most general network you can. They can generalize the best. And So that's it for this video. Hope that stuff's useful for you, and hope you join me for the next one where we'll continue looking at classification, but multi-class classification problems. See you next time.